Okay, so last time we talked about confidence intervals, we said that the purpose of a confidence interval was to estimate the value of a parameter. And it might seem a little strange why we want to do that. I mean, a naive but reasonable question is to ask, why do we need a confidence interval? Presumably, we already have a sample. We have a sample estimate. So why isn't that sufficient for estimating the value of the parameter? And we saw the problem with just having a single value, just the sample estimate. So our motivation for the confidence interval was that the sample estimate, which we sometimes call a point estimate, it's a single value or a point that best estimates the parameter value. The problem with that is that the sample estimate alone does not give us a measure of how precise our value is. Remember, when we were talking before about estimates, we said, what is a good estimate? Well, it's similar to when you get a car estimate, right, for some sort of repair. The estimate should be close to the true value. And the problem is that value alone doesn't tell us how much potential error is in our estimate. So the solution to this is to take the value of our estimate. So this is the value of our sample estimate. It could be a sample mean, right, estimating mu. Could be a sample proportion, estimating pi. And what we're going to do is we're going to add and subtract an error bar, which is going to reflect how precise our estimate is. So on both sides, we're going to add and subtract some error bar. And this error bar has a name. It's called the margin of error, and people abbreviate it MOE. Okay. So I'm going to subtract and I'm going to add it. And so now what I'm going to get, rather than just estimating the parameter by a single point, I'm going to get an entire interval. And this is the confidence interval. This is where the interval part of the confidence interval comes from. So the confidence interval goes from the estimate minus the margin of error all the way up to the estimate plus the margin of error. We're adding and subtracting our error bar. And this is the confidence interval. So unlike the sample estimate, which is a point interval, the confidence interval is, so instead of our sample estimate, which is a point estimator, okay, the confidence interval is an interval estimator. It's saying that we think the value, the true value of the parameter is somewhere in this interval. And so this seems reasonable. You hear about confidence intervals every day when you're listening to polls. But the question is, how do we get this margin of error? And what does confidence mean? So we want to address both of these issues today. And in doing so, we have to understand how the confidence interval is actually constructed. So I'm going to go into section 2 now of the text, which is called the logic of how a confidence interval works. Now, rather than try to give you a really very vague, general, theoretical description, what I'm going to do is I'm going to start off with a very specific, concrete case. And we're going to see how to construct the confidence interval for this specific case. And then once we understand how we did that, we're going to kind of reverse engineer that and figure out how to do it in general. So I'm going to start off with a definition. So I'm going to say that a 95% confidence interval for a parameter the way I'm going to get that, okay, what that means is that means I'm going to find some fixed margin of error so I'm going to find a specific margin of error. In other words, I'm going to find a specific value for that error bar. And what that 95% confidence, where that comes in, is what that means is when I put that fixed margin of error around the estimates from 95% of the samples, they're going to contain the actual parameter value. Okay, I'm going to find a specific margin of error, and what's going to happen when I have a 95% confidence interval is that for 95% of the samples of the same size, their confidence interval will contain the parameter value. All right. And admittedly, this won't make a lot of sense right now, but I'm going to go through this example, and after I do, you'll see how this all ties together. So what I'm going to do is I'm going to make a 95% confidence interval for the population mean. So what we're going to do in this example is I'm going to consider random samples of size n. They're all going to have the same size. And what I'm going to do is I'm going to find the 95% confidence interval for the population mean of some quantitative variable that I'm measuring from those random samples. Okay. Now, where we start from, the rational basis for how a confidence interval or why a confidence interval works is the same as hypothesis testing. It's the central limit theorem. And that's why the central limit theorem, in a sense, is kind of like the workhorse of statistics. It's really the foundation for any sort of thing that we want to do practically. So what I want to do is I want to consider what the sampling distribution of sample means from random samples of size n look like. And so if I think about what the central limit theorem tells me, the central limit theorem says that sample means are going to have a normal distribution. They're going to be centered at mu, okay? This headset's kind of hard to deal with, all right? So I'm looking at the population of sample means. So I know that the sample means are going to have a normal distribution with a mean of mu and a standard deviation of the standard deviation of the variable divided by the square root of n. And what I'm going to do is I'm going to construct a little sketch for the normal distribution like we always do. Standard deviation is like a ruler, right? So these are units of standard deviation. And my distribution will look like this. something like that. And now what I want to do, I'm going to use this as my confidence interval, okay? I'm going to center it at wherever the sample mean is, and this is going to be the margin of error. And I'm going to make a claim now. Here is my claim. My claim is that the margin of error for a 95% confidence interval should be twice the standard deviation of my estimator. So this is a claim. So I claim that if I let the margin of error be 2 times the standard deviation of the estimator, this will give me a 95% confidence interval. Now I want to prove that this is true. So I'm going to claim that this margin of error gives me a 95% confidence interval. So let me step you through this little construction here, okay? So this is a confidence interval, and you can see the margin of error here is 2 standard deviations. Okay, it goes exactly 2 standard deviations. All right. And what I want to show is that using this margin of error, for 95% of the random samples I can draw from this distribution, this confidence interval is going to contain mu. It's not a bad idea to kind of try this yourself, okay? Sketch out a normal distribution, make a little piece of paper, of equal width on both sides, and try this exercise at home. It will help you understand what's going on. So here's what I'm going to do. I'm just going to try some points, okay? Suppose I reached in this bag of random samples and I drew a sample mean that was out here. Okay, so this is my mu hat. We'll call this mu hat 1. This is the sample mean from a first sample I drew. Does the confidence interval contain mu? Does it contain the parameter? The answer is no. Okay, so the confidence interval doesn't work here. It doesn't contain the value of mu, right? It only goes out, it's a little hard to do, it's like playing Twister here. It only goes out this far. It doesn't contain mu. So the confidence interval does not work for this point, okay? What about this point? Suppose I try maybe this point right here. Okay, we'll call this mu hat 2. This is the mu from my mu hat from my second sample. And I put the margin of error around that estimator. Does it contain my parameter value? The answer is yes. So the confidence interval works here. Now the question is, for which sample means will this confidence interval contain the population mean? And you can kind of see pretty easily if you just play around. I'm going to center the confidence interval at the population mean, and I'm just going to keep sliding it over and over, and we can see that eventually when we get 2 standard deviations away, the endpoint of the interval just contains the population mean. And so what we see is we see that for all of these values that are 2 standard deviations away, the confidence interval contains mu for all of these sample means. Now here's a question. How likely am I to get a sample mean 2 standard deviations away from the population mean? Well, this is nothing more than the empirical rule. Okay, the population mean is the mean of my population, and we know that 95% of the values are within 2 standard deviations of the mean. So I know that 25%, I know that 95% of the mu hats are in here. So this establishes my claim. There's a 95% chance I'm going to get a sample mean in here, and for each sample mean in here, it is going to contain the parameter value. Therefore, this means in toto, there is that for 95% of my samples, this confidence interval will contain mu. Okay. So for 95% of the samples, this confidence interval will contain mu. And that's the definition of a 95% confidence interval. I'm going to find some margin of error such that for 95% of the samples, when I put that margin of error around it, it's going to contain the true parameter value. So notice what this 95% is. It's a measure of reliability. It tells me the percentage of samples my confidence interval will work for, i.e. will contain the actual parameter value the way I want it to. Okay. So now I actually know what the 95% confidence interval is. So we find out that the 95% confidence interval for mu is going to be equal to mu hat minus the margin of error, which is 2 times the standard deviation. So sample estimate minus twice the standard deviation of the estimator, which is sigma divided by the square root of n, all the way up to mu hat plus the margin of error, which is 2 times the standard deviation of the variable divided by the square root of n. Okay. So this is a 95% confidence interval for mu. Now, there's one little correction we have to make here, and that's regarding the use of the population standard deviation for the variable. If we think about it logically, it's very unlikely we could know this value if we're doing a confidence interval. And the reason why is, if we think about what the standard deviation is, the standard deviation is the average distance from the population mean. Well, if we don't know the population mean, how can we compute or how can we estimate what the average distance is from the population mean? Which is the same as saying, how could we possibly know the population standard deviation? And so if we're honest about it, we realize we really can't use the population standard deviation. So what should we do? Well, we have a sample. So why don't we use the fact that samples estimate populations? Why don't I estimate the population standard deviation by using the sample standard deviation? Okay? So I'm going to modify this slightly. So you could think of this as like a modified central limit theorem if you want to. And yes, there's a little bit of a problem with this. It's not technically 100% correct. However, when we're dealing with large enough sample sizes, and we're generally dealing with sample sizes of at least 30, it turns out that this approximation is actually a really good one. It's not bad. So it's acceptable. Okay, so now we see the logic of how we get a 95% confidence interval. Okay? Now we're going to switch gears. We want to ask the following question. What if we didn't want a 95% confidence interval? What if we wanted to have a different percentage for our confidence? So this is going to kind of bleed into this concept of what we call a confidence level. So the confidence level is the percentage of times that we want our confidence interval to contain the population parameter. So this is the percentage of samples whose confidence interval will contain the parameter value. So 95% confidence interval, it was a confidence interval where for 95% of those random samples, that confidence interval was going to contain the parameter value. But just like alpha, or the significance level in hypothesis testing, which could have other values, right? We usually use 5%, but we could use 1% or 10% for alpha. The same is true for a confidence level. We can have different values. So for the confidence level, there's a number of values we could have. We could have a 90% confidence interval, a 95% confidence interval. Sometimes people use 98% confidence interval, although it's not that common, and a 99% confidence interval. So these are the typical confidence levels that we can use when we're constructing confidence intervals. And we just saw a second ago how to construct a 95% confidence interval. We said use the margin of error that's twice the standard deviation of mu hat. So now we know how to get the margin of error for a 95% confidence interval. But suppose I said to you, I don't want a 95% confidence interval. I only want a 90% confidence interval. The question is, what would the MOE be for a 90% confidence interval? And what I want to do is I want to show you now, using the same sort of logic we used to get the MOE for the 95% confidence interval, how we're going to get the MOE for the 90% confidence interval. So what I'm going to do is I'm going to sketch out two normal distributions on top of each other. The first is going to be the normal distribution for the sample mean, which is just like we had before. Again, I'm stepping out in units of standard deviation. Okay. And the other distribution that I'm going to sketch is the standard normal distribution, which you remember is a normal distribution that has a mean of 0 and a standard deviation of 1. So this is what a standard normal looks like. And you might remember we said that the standard normal is actually the distribution that the z-scores make for any normal distribution. Okay. So now we want, I'm recording, sorry. So now I want to get a 90% confidence interval here. So here's what I'm going to do. I'm going to think about, how did I get the 95% confidence interval? Well, what I did was I found the two values symmetric from the mean that contain 95% of the population. So here what I'm going to do now is I'm going to find the two values that are symmetric about the population mean that contain the middle 90% of my population. How do I find that? Well, I'm going to use this kind of logic that we used before in chapter 7, right? We said, okay, if we have 90% in the middle, there's 10% in both tails, and each tail, because it's symmetric, has 5%, right? So I know this value that I'm interested in is really the 5th percentile for this distribution. Notice I can't find it using Excel. I could try to use norm.inv, but the problem I would have is that I don't know the mean. So the solution is I'm going to use the standard normal. And now I'm going to use a very important fact, and this is the fact that we talked about before. That is, if we take any value from a normal distribution and its z-score, they have the same percentile. So I'm going to take this data value and I'm going to take its z-score, and its z-score has to have 5% in the tail. Okay. All right. So the z-score for whatever this value is has to be the 5th percentile also. And I'm going to use the fact that there's a relationship between these two values, right? If I think about it, this data value x is equal to mu minus z times the standard deviation. Okay? And notice what I'm interested in is I'm interested in this. This is the distance from the mean. So if I can find this z-score, I multiply it by my unit of measurement, standard deviation, and that will tell me how wide to make the margin of error. Okay, so the observation here is that x minus mu, okay, is going to be the margin of error, and this is going to be whatever this z-score is down here times the standard deviation of the estimator. And that's how we're going to get the margin of error. Now, I don't know how to get this value, but I do know how to get the z-score, because I know since this is the z-score for this data value, it has to be in the 5th percentile. And I know the mean of this normal distribution and its standard deviation, and if I have a percentile, I can figure out the z-score. So this z-score is going to be norm dot inv. I'm going to put in the percentile. It's 0.005. I'm sorry, 0.05. The mean, of course, is 0. The standard deviation is 1. And we know how to compute that in Excel. And it turns out if you put this in Excel, you'll find out the number is roughly about 1.645. It's going to be negative, but we're always going to take it to be positive. So I can make it positive, right? Or if I wanted to, I could use a 95th percentile, which would automatically return a positive value. So now I know how to get the margin of error for the 90th the 90th percentile, okay? I mean the 90% confidence interval. So the margin of error here is going to be 1.645 times the estimated standard deviation of our estimator. And so here's really the key thing that we want to note in general. In general, what we want to note for a given confidence level, the MOE is equal to a z-score, and that z-score is going to be the absolute value of 1 minus the confidence level divided by 2 times sigma hat divided by the square root of n. Okay? It's going to be a z-score times the standard deviation of the estimators. And this z-score, this is how we compute it. I take the confidence level, subtract it from 1, and divide it by 2, right? 100% minus 90%, 10%, divided by 2, and it's 5%. So this is the logic behind how a confidence interval works. And we're going to spend a lot of time talking about how to do it for specific examples. We're going to spend a little more time talking about the interpretation of confidence intervals, how to get sample sizes for a given level of precision and whatnot. But hopefully this gives you an idea as to where this z-score comes from.